Divisibility and modular arithmetic. Modular arithmetic has a lot of applications in computer science and in mathematics. And it is a very simple concept, but it is also a very important concept. The whole idea depends on a division of an integer by another positive integer, and then we care about the remainder. If we have two positive integer, negative or positive, and we want to divide it on a positive integer, then we get a remainder. We are interested in that remainder. It has a lot of indications about the integer we divided. We will see. So working with the remainders leads us to what's so-called modular arithmetic. Modular arithmetic. And this modular arithmetic plays an important role in computer science and in mathematics. And it is a very simple concept, as I just said. So let's go for it. To understand it, first we go with to recall what division means. If we want to divide b integer over a, so that a does not become 0, is not 0, so that we don't divide over 0. We will say a divides b, written this way, if simply b equals a times some integer, which means I like this one more. b over a is an integer. Then we will say a divides b. And in such a case, we call a factor or divisor of b. So a divides b, so it is a divisor or a factor of b. And we call b a multiple of a multiple. As we see here, multiply a with a c, we get b. So b is multiplying a with some integer, so it is called a multiple of a. And whenever a does not divide b, we will write it this way. To make it more clear, this is a does not divide b. A does not divide b, we write it this way. Okay. Now we have a nice example here. It gives you two integers, n and d, and it says how many. So let's see, we have integer n and d. It says how many positive integers not exceeding n are divisible by d. So we have two integers, n and d, and we are asking how many integers less than n and divisible by d. We want to find how many are there. But let us ask first, what are the integers? How did they look, the integers that are divisible by d? They are actually multiples of d. It is d itself, 2 times d, 3 times d, 4 times d, 5 times d, and so on till we reach n, or a little before n. What do I mean by reach n or a little before n? The better way is to describe it using a number line. So assume 0 is somewhere here, and this is one copy of d, 2 copies of d, and assume n is somewhere here. We are assuming n is greater than d now. Okay, now we will keep taking copies of d all the way. And these are the integers that are divisible by d. The integers that are divisible by d are multiples of d, and multiples of d takes this form. And we will keep going till we reach some point here, which is k times d, so that if we take the multiple of d that comes after, which is k plus 1 times d, then we find ourselves has jumped over n. We have exceeded n. Okay? So this is the idea. I keep taking multiples of d till I get a little before n or on n itself. And then the next jump will take me after n. So these are the multiples of d that we are asked to find how many, the number of them, how many they are. Okay? So can we count them? It is k. What is k here? So how many of them are there? So the idea here is, what if we divide? So let me do something interesting, good. Let me call this distance r, and this distance is less than d, okay, because one more jump of d take us after n. So the distance between n and kd is some r, and then r, it might be 0, but indeed it must be less than d. So what we have done in here, write n, so divide n by d, and then the result will be q plus the remainder. The result will be k, I said q, this is k, plus the remainder. And again, the remainder is between 0, greater than or equal 0, but it is less than and not equal to d. So the number we are looking is k. Can we obtain it here? Note, if we divide n by d, then the result is k plus some part which is less than 1. So actually, if you think about it, k is the floor of n over d. So how many copies there are of d between 0 and n is simply divide n over d and take the floor. Okay? So this answers our question. We move to the theorem, where this is trivial theorem that you know. If we assume a, b, and c are integers, and a does not equal 0 because a is a divisor, and 0 divides no number, right? Okay. If a divides b and a divides c, then a divides their addition, correct? Let's prove that here. A divides b means b equals a times s for some integer s. This is the definition of this divisibility we have just seen. Also, a times c means c equals a times t for some t belongs to z. Now we want a to divide b plus c. So b plus c equals a times s plus t. So b plus c is a multiple of a. It is a times this integer. And that simply gives that a divides b plus c. So if a divides two integers, then it divides the summation. Okay. Part B of the theorem. If a divides b and a divides b, then if a divides b, then a divides bc for all integers c. To prove it, a divides b means b equals as for some s belongs to z. And now we want to show that BC is a multiple of A, so B times C is A times S times C. So this is a multiple of A. And that simply gives A divides BC. This is so easy. Okay, part 3. If A divides B and B divides C, then A divides C. And I will let the proof for you to work out. It is the same thing. Now this is part 4. It is a corollary, but I wanted to add it as a part of this theorem. And to prove part 4 is important, is very important actually. It says if A divides C, B, and A divides C, then A divides MB plus NC. Simply, that means if A divides two integers, then A divides any linear combinations of these two integers. The two integers are B and C. Now multiply B by some M integer and C by some N integer and then add. This is called linear combination of B and C. So to prove that, same thing, we will assume that we have this information here. Okay, and we will use them. Now we want to show M times B plus N times C is a multiple of A, is a multiple of A. Okay, so this is easy. MB times NC equals, so B is A times S and C is A times T, so we will get M times AT plus N times AS, and this simply A times MT plus NS, and then we are done. So what we got, this number here is A times another integer, so it is a multiple of A, which means A divides MB plus NC. This is, especially part 4, is easy, and it is very important actually, very, very, very important when we do working with integers or in modular arithmetic. Okay, now we go to division algorithm. You know this since fifth grade or more or earlier. It is simply about if we want to divide A by D, okay, and we want D to be positive integer. So recall that D is positive, and D here is called the divisor. We will divide A over D, and we always want the divisor to be positive here. Okay. Now it simply says divide A over D. Here we go. The result is Q, and the remainder is R. So this is the definition. And the remainder is always less than the divisor, and it can be 0. So it is between 0 and the divisor. Okay? So these are naming. A is called dividend, maqsoom. D is called divisor, qasim. Q is called the quotient. I called it the result of the division. And R is the remainder. Okay? This is the division algorithm. قسمة طويلة. We know it. Simply do long division. You can divide any number by any other number. Let's do it for just fun. If we want to divide 43, let A be 43, and let D equals 5. Then simply 43 equals 5 times 8 plus 3. So this is Q, this is R. Simply. I just use long division. Okay? Let me do it again, but I will choose negative number for a. What if a equals negative 21 and b equals 9? Okay? Divide negative 1 by 9 and there will be a remainder. But the remainder must be non-negative. You are not allowed to give a remainder to be negative. So we will not think of doing the following. You might think it is negative 21 equals 9 times negative 2, negative 18, plus negative 3. Okay? No. This is not acceptable because the remainder, we want it to be positive. Okay? For some reason. So again, the remainder here or here, it is greater than or equal 0. Cannot be allowed to be negative. So we will go again for this and do it here. And rewrite negative 21 to be 9 times negative 3. That gives me negative 27 plus 6. Okay. Now this is Q and this is R and it is non-negative. Good? Okay. Now we will define, once we do this division here according to these notations, divide A by D and then the remainder is R. Okay? Then we will say R equals A modulo, this is written in bold, modulo D. Okay? So if I go back to these examples here, okay, good. I will write here that 43 modulo what? What was the divisor? 5, which is D. What was it? 43 modulo 5, which is the remainder, which is 3. It is R. And here, negative 21. I need some space here. Negative 21, okay, divided by 9. Okay, the remainder is 6. We will write it this way. So this is always the remainder. This is R. This is always the divisor. And this is the dividend. This or this. So I may go back here and say D here is the divisor. R here is the remainder. This is to emphasize this setup. A here is the dividend. Good. So we have done 2 examples, and I will let you think about these ones that are written here. They are similar. Dividing negative 11 by 3, the remainder is 1. Dividing 101 by 11, the remainder is 2. Okay? And remember this notation. R equals A mod D. And the mod here is written in bold face. Okay. And it is the remainder. It's all about the remainder. Now we will define another version of mod. We will say 2 integers, A and B, and we will have assume fix. Let me say here that start with an M. Fix it. So fix nm. Now, two integers a and b will be called congruent modulo m. So the congruent must be related to some integer modulo m. And we write it this way: a, three lines, b, and the modulo here is between parentheses. Okay? And we will say this is a congruence. This equation, this kind of equation is called a congruence. When all that happen, whenever m divides a minus b. Here we go. M divides a minus b. So we have, if m divides a minus b, then we will say a is congruent to b modulo m. And if we say a is congruent to b modulo m, that means m divides the difference between the two integers. Divides a minus b. Okay? So, two integers are congruent modulo m if the distance between them is a multiple of m. If the distance between them is a multiple of m. For example, if we choose m to be 5 and then we go to the number line, I will say this is 1. Give me an integer which is congruent to 1 modulo 5. I would just move a distance of 5. Give me another one. I will move another distance of 5, which is 11. One more. Another distance of 5. Good. Now I can see here 1 is congruent to 6. I will use a parentheses here, modulo 5. So we are using parentheses. I will say also 1 is congruent to 16, modulo 5. I will say also 6 is congruent to 11, modulo 5. Or 6 is congruent to 16, modulo 5. Simply because the distance between any of these two integers is a multiple of 5. And if we want to have more fun, we can go this way and then say, oh, okay, I can add negative 4 to here because the distance between negative 4 and 1 is 5. So I can say also negative 4 and 1 are congruent modulo 5. And negative 4 is congruent to any other integer that we see there. I can say 11 is congruent to negative 4 modulo 5. And so on. Okay? So two integers are congruent modulo m if m divides the distance between them, or if the distance between the two integers is a multiple of m. Okay. Now this theorem here, it gives us a way to recognize whether two integers a and b are congruent modulo m. This says if and only if the following happens. A boldface modulo m is the same as equals b boldface modulo m. But remember, what does that mean? All this, what does it mean? And all that, what does it mean? It means the remainder. This one here means the remainder after dividing a by m. And this one here means the remainder after dividing b by m. Okay? So this theorem says two integers a and b are congruent modulo m if and only if the remainder after dividing by m for each one of them is the same. So this is what we are saying here. A and b have the same remainder when divided by m. So the whole, I should give this green, the whole, this equals what I circle in green now. So when you see such a thing, remember, when you see such a thing, it's a remainder of dividing this integer by this integer, okay? Again, I will write it somewhere here When I say the remainder of dividing a by m, I will write it this way, a modulo m. Okay? The remainder of dividing c by s, I will say c modulo s. So get used to that notation. Okay? When you see it, it is simply the remainder. Okay? When divided the integer that comes first by the integer that comes after the mod, the mod. Okay, and the proof of this theorem is exercise. It is direct, very direct. Okay, now the theorem we have just talked about, it is the very same theorem as here. It says again, two integers a and b are congruent modulo m if and only if what? If and only if there is an integer k such that this happens. Like it looks like this is a joke, right? Why? Because this says km equals a minus b. Wow, but this means m divides a minus b. So we are adding nothing. But we know this happens when this happens. Okay? So we are adding nothing, just giving it a different form, introducing an integer k. So this is easy. Good. Now we have this theorem. It says if I have two integers congruent modulo m and some other two integers congruent modulo m, if I add these two, it would be the same if I add the other two. What's about multiplication? The answer is yes. Now, this is what says, if A and B are congruent modulo m, I look at them as they are equal if I think about modulo m. And C equals to D if I think about modulo m. Do you know what I'm saying? Why I'm saying that? Like if we have integers, just integers. Let me see that A, B, C, let me assume. These are just integers. You know that if A equals B and C equals D, then simply direct conclusion that if I add these two and I add these two, I get equality. A plus C equals B plus D. And if I multiply them, also I get equality. And this is what we are seeing here. If we add A to C, here we go, and add B to D, here we go, we still have congruence modulo m. The equality still happens. Or if we multiply them, we will still have congruence modulo m. It is very similar to this property. It is the same property, but no, here we are working modulo m. And this will help us to do modular arithmetic. So the title of the section that we are working on is called Modular Arithmetic. Arithmetic means we want to do computations, multiply, add, take to power, subtract, do something like that. This is arithmetic. But we want to do it according to some modulo. That's why we call it modular arithmetic. It is the same as arithmetic in Z, addition, multiplying, subtracting, raising to power. We will do the same thing modulo m. And the properties of doing arithmetic in Z will be reflected. They will be the same properties when we do arithmetic modulo m, when we do modular arithmetic. That's what we are saying here. And we will see how that will happen. Okay. Corollary. If you look at the notation of this corollary, it looks kind of confusing. But it is very simple, actually. Very simple. Let me ask you, if you have two integers, a and b, and you want to divide by m, okay? I want to ask about the remainder. In the following two cases, I want to ask that if I add a plus b, I get a new integer. Divide that new integer by m, and then you get remainder. Put it here. Let's go the other way. divide a by m and take the remainder, divide b by m and take the other remainder. So we have two remainders. If we add them, okay, shall we get the same one here? If we add them, we might get an integer greater than m. Okay, divide it by m and take the remainder again, and then the result, this result here, it will be the same one here. So let me explain it. If I add two integers and then take the remainder with respect to m, okay, this is the same as take the first integer, take the remainder of the first integer, and then take the remainder of the second integer, okay, and then add these remainders. So these remainders might be greater than m. So what I do next in such a case, I will take the remainder of this remainder with respect to m, and it will be the same. An example will make this very clear. Let us assume a is 14. B is 23. M is 5. Okay? Now add a plus b. A plus b. Which is what? 27, right? Okay. A plus b. Take the remainder after dividing by 5. What is it? 27 divided by 5 is 5, and the remainder is 2. So this equals 2. Okay? So what we have done here, we performed or computed the left side of the equation. Now let's go to this side here. First, I will take a modulo 5, which means the remainder of dividing a by 5. But a is 14. So the remainder is 4. Okay? And take the remainder of dividing b by 5. b is 23. So the remainder is 3. Add them. What we get? 4 plus 3. Right? Now what we do? Let me use blue color. And go back to these parentheses and give it blue color. Okay, now what I do? Parentheses with blue color. What I do? Take modulo 5. So it is here. So I will take modulo 5. So what does it equal? This is 7. 4 plus 3 is 7. So I got 7 modulo 5. And in here I got 2. Are they the same? Yes, they are the same. Okay? And here we use equal with 2 lines, not 3 lines. We use 3 lines when we take modulo m with the parentheses. Okay. So we got it. So this illustrates the first part of the theorem. The second part is the same, exactly the same, but replacing addition by multiplication. So if we multiply the two integers together, take the result. Divide it by m, take the remainder. Or start with the first integer, take the remainder with respect to m. And the second integer, take the remainder. So we get two remainders. Multiply them. Take the result. And take the remainder modulo m again. Then the resulting here will be the same as the remainder of dividing a times b modulo m. It will be the same thing. So I will let you make an example for this. And I will help you by giving the example. Choose a to be 9. Choose b to be 8. And again m to be 5. So work the example and make sure this part indeed is true. Okay? So good. So it doesn't matter. Shall I add two integers and take the remainder, or multiply two integers and take the remainder? Or take the remainder of each one of them first and then multiply or add. It does not matter. Do it the way you like. And this will make computations easy for us. And now all what we have mentioned in the theorems above will be applied in this example. 37. So I need to go to fix that. I said 27. Where? It is. I did not write it. Okay. It is 37, but the remainder is still 2. Okay. Thank you. Okay. Let's do computations. And to make sure that you understand the notation. Okay. Now it says the following. Take 19 to power 3, okay, divided by 31, and then take the remainder. Good. Once you take it, raise it to power 4, and then take the remainder with respect to 23. Okay. So first thing we need to do is to find out what is 19 to power 3. 19 to power 3 is this number. Now what we do with it? We take the remainder of this number after dividing by 31. And this is the remainder here. So, 19 to power 3 modulo 31 is 8. The remainder of dividing 19 to power 3, 19 cubed by 31, this is the remainder. What next we need to do with that? So, I will give this green. This is this part. So this part now, we need to raise it modulo 4. So we will go to 8 modulo 4. So 8 modulo 4 is this number. We will take it modulo 23. So we will divide this number by 23. So I will give this purple now and this purple. And then this is the remainder. So 8. So I don't need one of these. I'm copying. Okay. 8 to power 4 divided by 23, we get 2. Okay, good. So what we got here, if we go back, this is replaced by 8 to power 4, okay, which is 2. Okay, we got it. So actually here, we use the two theorems we have seen implicitly. Okay? Either of taking 19 times 19 square, and then take it modulo 31, and then we get that, we multiply it by 19 again, and then take modulo 31 again. Instead of doing this, we multiplied 19 by itself 3 times. So we have used the theorem we have just seen above. Okay. And this is the only example. There are similar examples in the exercises that you need to practice. It is important you practice on that. And at the end, we will mention now arithmetic modulo n. We will see these notations later. What we mean by this set, z sub m, all the integers from 0 to m minus 1. And there is a reason to choose that. If you take any integer, negative or positive, big or small, divided by m, then the remainder shall be between 0 and m, but not equal m, which I mean the remainder can be 0, and it is an integer, and it is less than m, right? So that means the remainder is 0, 1, 2, 3, all the way to m minus 1. So this is why we are choosing this set. It represents the remainder of dividing any integer by m. Okay? Now take any integer, divide it by m, take the remainder, it will be there. That means any integer you take is congruent to one of these integers inside m. Okay? Okay? For example, let me make it clear by doing an example. Z5 is 0, 1, 2, 3, and 4. Okay, take an integer, 5672, divided by 5. The remainder is 2. It is there. So that the number I said, I don't remember what I said, is congruent to 2. Take another number, 1073. Remainder after dividing by 5 is 3. So that number is congruent to 3, and 3 is there. Take another number, 174. Divided by 5, remainder is 4. So it is congruent to 4. Take a number, 2,002,500. Divided by 5. The remainder is 0. So that number is congruent to 0. Take any other number. Let's take a negative number. Take any number. You will find it congruent to one of these, modulo 5. Take a negative number. Take a negative 163. Okay. This is congruent to what? It shall be congruent to one of these numbers. Okay? Remember what we do? We will write, we will divide this by negative 5, and then the remainder will be negative 3, but be careful. Okay? Then do it this way. You know, negative 160 divided by 5 is 32, so negative 32. But if I write it that way, I will get plus negative 3. I don't want negative 3 to be there. So I will say negative 33. I will say negative 163 is 5 times negative 33, and that gives a negative 165. So I need to add 2. Oh, okay, so this is congruent to 2. So any integer must be congruent to 5. To one modulo, any integer modulo 5 must be, let me say the statement more. Any integer is congruent to one of these modulo 5. This is better to say it this way. Okay, now I gave you a reason why we study ZM. And inside ZM, when we add, we will use this notation. For example, 4 plus 4 modulo 5 is 3, right? Because 4 plus 4 is 8, and 8 is congruent to 3. And I will write here 4, let me separate that, times 3, but this now times modulo 5 is 3. You agree with that? Because 4 times 3 is 12, so I need to fix that. 4 times 3 is 12, modulo 5 is 2. Okay? And if I say 4 times 4 modulo 5, that is 1. Interesting. Okay. Good. And guess what? 2 plus 3 modulo 5 is 0. 2 plus 3 is 0. Yes, it is 0. We are working modulo 5. So we will introduce this notation, and it is defined in here. Just add, multiply a plus b modulo 5. Add them as integers, a plus b. You get a new integer. Divide it by m. Take the remainder. A times b modulo m. Multiply a and b as integer. Normal, regular multiplication. You get a new integer. Take the remainder of it after dividing by m. And then you get that. And these are called addition and multiplication modulo m. And now we have seen example above there. And I will let you have a look at this example by your own. Work them. And at the end, we will go over these properties. Now, if you notice what I said, if you want to add 2 integers modulo 5, take the 2 integers, add them as normal integers, and get whatever you get as an integer, and then take the remainder modulo 5. Same thing for multiplication. So basically, when we do arithmetic addition multiplication modulo m, we basically are doing this arithmetic inside Z, and then come back, take the remainder modulo m. And we have just seen in the two theorems above there, it says you either to do the modulo, I mean two integers, want to add them, you either take the modulo of this integer, take the modulo of this integer, and then add, and then take the modulo again, or take these two integers, add them in z, take a new integer, take the modulo. Either way, it is good. So what's happening here now, computing inside the modulo is translated to computing inside z with regular addition and multiplication. After we are done, we take the modulo. That means the properties of arithmetic inside z will apply here. You know that one of the properties that if you take two integers, add them or multiply them, the result is an integer. So a closure. So first thing is a closure. So if you take two integers, add them modulo m and multiply them modulo m, and then the result will be here. Because if you take the two integers, add them or multiply them, and then take the modulo m, it will be congruent to one of these integers. The result of the addition and multiplication is a new integer. And I said any integer has to be congruent to one of the numbers of zm, 0, 1, 2, all the way to m minus 1. So it is a clause under multiplication. Associativity. Okay, it says here, does it matter if I add the first two modulo m and then do it take the result and then go modulo the third integer, or I do the modulo the computation for the last two integers, then when I am done I go to do the result with the first integer. Does it matter which two I choose? It does not. It does not. Because you know, if you add three integers, 3 plus 2 plus 5, it does not matter which two you add first. Okay? Because this property is coming from z. And same thing for multiplication. If you multiply three integers, it does not matter which two you multiply first. And that thing is reflected to computations modulo m, to arithmetic modulo m. And computivity, it does not matter if you say a plus b or b plus a, or a times b or b times a, it does not matter. And the identity element, 0 plus anything is that thing, it does not matter. And the identity here, it says identity of addition, identity element of addition, and here is the identity element of multiplication. So basically we have the same properties of the arithmetic in z. When I say arithmetic in z, it's just the ones you learned in elementary school. Additive inverse. This is interesting, you need to know it. Additive inverse. If we work in z, just z, what is the additive inverse of 2? It's negative 2, because 2 plus negative 2 is 0. But what is the additive inverse of, in the example we have seen, what is the additive inverse? You need to pay attention to that. Of 2 in z5. Is it negative 2? Okay, negative 2. But negative 2 is not a member of z5, right? Because z5 is simply 0, 1, 2, 3, 4. So negative 2 is not there, right? So what negative 2 has to be one of these, 0, 1, 2, 3, 4. Which one of them is negative 2? Actually, this one. This one is congruent to negative 2 modulo 5, because the difference between them is 5. So actually, if we noticed a little ago, 3 plus 5, 2 modulo 5 is 0. So 3 is the additive inverse of 2 in z5. Interesting, huh? What is the additive inverse of 4? It is 1. And the additive inverse of 1 is 4. And the additive inverse of 3 is 2. Okay, now it says general rule how to find the additive inverse of a. Here, this is a. Add what to it to get 0? Add m minus a. This is simply When you add them as integers, a plus m minus a, it is m. But m is 0 inside the m. Okay. Distributivity. Distribute this over that, we get a times b plus a times c, and this operation, you know, distributive, these operations come here. And same thing happens for from the left or from the right. And you know these things happen with integers, so it also happens there. And at the end, we will say that multiplicative inverses do not always exist in Z, in modulo M. For example, if we have C6, Z6 consists of 0, 1, 2, 3, 4, 5. Okay, now we are talking about multiplicative inverse. In here, we talked about additive inverse, and every element has an additive inverse. Give me an A, then the additive inverse is M minus A. Now, if I ask you about multiplicative inverse, which means I give you an element, then I want another element that if you multiply by this one, the first one, we get 1. Okay? Now, what's about 2? 2 does not have a multiplicative inverse in Z6. Does not have a multiplicative inverse in Z6. 2 does not have a multiplicative inverse in Z6. How do we know that? Well, if it does have, then it has to be one of the elements, right? So multiply 2 by every one of these elements. Multiply 2 by 0 is 0. 2 by 1 is 2, is not 1. 2 by 2 is 4, okay? Is not 1. 2 by 3, modulo 6 we're working, is 0, is not 1. 2 by 4 is 8, modulo 6 is 2. 2 by 5, modulo 6 is 4. And we said 2 by 0 is 0. And we said 2 by 1 is 2. And 2 by 2 is 4. And we are working modulo 6. So none of these elements of these 6 multiplied 2 into 1. So 2 has no inverse there. Okay. And this is the end of the lecture. And thank you.